Back when we had just two dimensions, we talked about what it meant to have different numbers of solutions. So we're going to continue that conversation now that we have a third dimension that we're talking about in terms of geometry. So, no solution is the easiest case. You notice that there's no place where all of them intersect. So at the top you see here's a two-dimensional case where the lines are parallel. Here's a two-dimensional case where they're not both linear, but the point is that they're never intersecting. Here's the most obvious case of three dimensions where you have three planes that never meet. But it's also true that if they don't all meet in the same place, it's still not considered a solution. So this is not considered a solution because it only solves two of the equations. It doesn't solve this third green plane. So two planes being parallel and the third one cutting through them, it's still no solution because the orange and the green planes never meet. It's even possible for any pair of them to meet, but for them not to create a solution, because this line, and that line are all parallel lines, and there's no place where all three of them intersect. So there are multiple ways we can have no solution in three dimensions. Now, what does this look like in terms of if we solve something? Well, if we have a matrix and any one of the lines has zeros on the left and then 1 on the right, that means that 0 plus 0 plus 0 equals 1, and that's false. Or 3 equals 7 if we're solving it without a matrix. These false statements give us no solution. One solution is what we see most often, and with three dimensions and planes, you see that these three planes meet at one point, which is usually what happens. Two lines usually meet at one point, and if you use other shapes, as long as they only meet at one point, it still is a one solution system. In terms of a matrix, it would look like this, where when we solve this, the square matrix looks like the identity matrix, and then it doesn't matter what's in the right column because this is the identity matrix. When we solve it algebraically, we get x equals 2, y equals 5, and z equals 1, or some other triple if we're in 3 dimensions. If we're in 2 dimensions, we're only looking at 2 variables. It's possible to have more than one solution without it being infinitely many solutions. So for example, here we have 2 solutions between y equals x squared and y equals sine of x, because it crosses here and here. So 0, 0 is one point of solution, point where they intersect. And at that point, those are the approximate values of that coordinate. It's not possible to do this with linear equations. It's not possible to do this with planes in 3 dimensions. But if you use nonlinear things, you can get 2 points as a solution set. What does it look like when we have infinite solutions, but it's not a whole line or a whole plane? And this is what we saw when we dealt with general form of trigonometric solutions, where we had sine. Here's the red line is y equals sine of x, and the blue line is y equals 1/2, and it's very obvious to say that they meet at pi over 6, and they also meet again at 5 pi over 6. But then there are infinitely many solutions when we add 2 pi n to that. So here's another solution by subtracting 2 pi n from 5 pi over 6. Here's another solution by subtracting 2 pi from pi over 6. So this is what it looks like algebraically when you solve it. And when I say countably infinite, I mean that we can list them in order, even though it's still infinitely many. A line of solutions is when there are infinitely many and it's the entire line or the entire curve. So here this black line and the red line are in the exact same place, so that's infinitely many solutions. Here, these three planes all meet in the same line. And it's also possible to just have two planes meet in one line. Typically, actually, two planes will always meet in a line unless they're parallel planes. And there's a number of ways that this can look. I'm going to focus on the three-dimensional case. This is an example of a matrix which has infinitely many solutions and describes a line. You'll notice that there's one completely empty row once we do this, and this is represented by having one of our equations in parametric form be y equals t or z equals t. Then whatever that is gets substituted in. So this is y plus 3z. Actually, this should be minus. Yeah, that makes more sense. And this should be minus t. And then that means that this should be fixed to be over -1, and this should be over -3. So here is a way of describing it in parametric form. Here's a way of describing it in symmetric form. It's also possible that y doesn't have any effect on this, and x equals 2, z equals 5 is a point in the xz plane, but if you add the y-axis, it's parallel to the y-axis. A plane of solutions in 2 dimensions, it's the entire coordinate plane, and this is just me shading in the whole grid. If we have 3 planes that all land on top of each other in 3 dimensions, then there would be a plane of solutions, and that looks like a matrix where all of the rows are empty except for the first one, and it looks like this: x plus 3y plus z equals 2. Yeah, that's how you can tell how many solutions something has. Thank you.